Okay, so welcome to this next video in which we are discussing entropy and the second law of thermodynamics. Okay, so we've just discussed the second law of thermodynamics. Now what we want to do is an example basically of a calculation where you see that the entropy of the universe goes up, and you can use this to justify why some processes do not occur and why others do. Okay, so we're going to take the example of water freezing. So let's say we have a little container here which contains water molecules. Okay, so there are loads of water molecules here. And I'll colour in the water molecules as blue dots. Right, okay, so you have water in this container, and let's say we have 1 mole of water molecules in this container. It will just make the calculations easier, okay? So 1 mole of water molecules in this container. So 1 mole is, remember, equal to 6.022 times, let me just bring this over a little bit, times 10 to the 23 molecules, the Avogadrian constant. Okay, right. So we've got 1 mole of water molecules in there. And now we know that if we take the temperature down to below 0 degrees Celsius, what will happen is these water molecules will freeze. And we want to try and justify this reaction. Okay, so we know that if the temperature goes down to below 0 degrees Celsius, if we lower the temperature of the lab down to below 0 degrees Celsius, what will happen is water as a liquid will go to water as a solid, basically. Now, we want to understand this in terms of the second law of thermodynamics. Why does this make sense? Okay, so how does water going from a liquid to a solid lead to the universe taking on a macrostate that has a greater number of microstates that are associated with it? So remember, the second law of thermodynamics says that overall the universe will go from 1 macrostate, so we'll say macrostate 1, okay, to macrostate 2, okay, over time, only if the total number of microstates that would all be seen as macrostate 2 is greater than the number of microstates that would all be seen as macrostate 1, i.e. only if the entropy of macrostate 2 is greater than the entropy of macrostate 1. That's the second law of thermodynamics. Okay, so we want to now try and justify this, because you might think, well, how on earth is, water turning to ice going to increase, this new macrostate is, well, let's just outline what the macrostate 1 and macrostate 2 are. So macrostate 1 is we have the water molecules as water basically in this room that's below 0 degrees Celsius. Macrostate 2 is that we then have these water molecules as a solid, okay? And we'll assume that the rest of the universe hasn't changed, so everything around hasn't changed, okay? So just to simplify this down, so we'll have them as water, and then it's going to solid. Right, okay. Now, there's a little bit more that has changed here. That is not all that's changed. If that was all that had changed, then this would not be allowed by the second law of thermodynamics. The reason this is going to be allowed by the second law of thermodynamics is that when the water turns to a solid, it's going to give out heat, basically. So this is an exothermic transformation. It's going to release heat, okay? So what's going to happen is when the water molecules convert to a solid, heat will be released, okay? And the heat, by the 0th law of thermodynamics, the heat will not just remain in the glass box, it will disperse out, and we can assume that it doesn't leave the lab. We'll say it just goes into the lab, basically. So we'll assume that, the heat isn't going to go off into the rest of the universe. Of course it will eventually, but we'll say we haven't left it long enough yet. We've just done it to the point where the heat is still within the lab. Okay, so it will now heat up all of the surroundings, which we are counting as the lab, basically. So you'll get the lab being heated up. Okay, so the temperature of the lab is going to be raised a little bit, and the temperature of the box will be raised a little bit as well. So the temperature is going to go up a tiny bit. Now this might not be noticeable, but it will go up a tiny bit. And basically that rise in the temperature of the lab and of this box is going to lead to a macrostate which has a greater number of microstates corresponding to it. So basically, macrostate 2 isn't just that the water is now a solid, it's also that the temperature is a little bit higher. Okay, we can measure temperature, we might just be able to detect this little change in temperature in principle at least. Okay, so we have these two macrostates, and basically the claim is that this macrostate 2, where you've got solid water as ice, and you've also got a slightly warmer room, has a greater number of microstates of the universe that all correspond to that than does macrostate 1, where you've got a colder room, but more, well, the water molecules are as water rather than ice. Okay, so we want to now understand how temperature, well, how adding heat to the surroundings is raising the entropy, basically. And it's because the temperature goes up. And if the temperature goes up, then basically that means that the average energy of a molecule within here must have the average energy must be greater, basically, because that's what temperature is. In a hotter room, the average energy of the air molecules is greater, basically. So, if the temperature is greater in this room, the average energy of the molecules is greater, and that means that the total number of ways that you have of distributing this energy among the air molecules is much greater. So, the total number of microstates of the universe that would all correspond to this macrostate 2 must be greater, basically, because of the temperature increase. I'm not yet saying that it's necessarily greater than macrostate 1. I'm just saying that the fact that temperature goes up in this room is going to mean that macrostate 2 has a higher entropy than if the temperature hadn't gone up. Okay, right. So now let's do some calculations, basically. We need to know how much adding a bit of energy into the surroundings is going to affect the entropy of the surroundings, basically. That's the equation that we don't yet have, okay? And basically the equation goes like this. That the change in entropy that the surroundings will feel is going to be equal to the heat that was released. So how much energy you gave the surroundings, okay, so that makes sense, but it's divided by the current temperature of the surroundings, okay, so temperature again in kelvins. Now, one way you could justify this equation is just by saying, well, look at the units of entropy. It can't just be heat, basically. The heat that you release, it's got to be divided by some sort of temperature term to make the correct unit. So there is dimensional analysis that can help you out here. But basically, intuitively, what this is telling you is that if you add a certain amount of heat to a system, okay, then the amount that will increase the entropy depends upon how much energy each of the molecules already has, which is the temperature. So remember, the temperature tells you the average kinetic energy of the molecules, okay? So if the temperature is very, very low, then you can imagine that if you add a bit of energy, that's going to trigger a much larger change in temperature than if the temperature is very high, and also it's going to lead to a much higher increase in entropy, okay? Whereas if the temperature is already enormous, then adding, a certain amount, the same amount of energy is going to have much less effect on the temperature, and it's also going to have much less effect on the entropy. Okay, so I hope that is intuitive. I'm afraid I can't really provide a derivation of this equation. I don't really know a derivation of it. But that is the equation that links the amount of heat that you release to the change in entropy, basically. So we know that the change in entropy of the universe, i.e. the change in entropy that you go through when you go from macrostate 1 to macrostate 2, and we're talking now about these states representing the entire states of the universe. We are assuming, of course, that everything outside of them doesn't change, basically. Imagine you've frozen everything else and all that's changing is what's in here, okay? So, delta S of the universe is going to be equal to the change in entropy of the system, so the change in this little box, plus the change in the surroundings. And in this case, we are assuming that, this water freezing here is not going to affect, some planet millions and millions of light years away, okay? So we're assuming it's only going to affect the surrounding lab, and that's an okay assumption to make. Okay, so plus the change in the entropy of the surroundings. Now, we need to know how much is the entropy of the system going to change. So that means how much is the entropy within this little box going to change. So when the water goes from being a liquid to being a solid, what will happen is, firstly, that will decrease entropy because, of course, all of the molecules are now in a tight structure, okay, so they're all bound together tightly, there's not much movement, there's far fewer ways that you can arrange them to see this same sort of solid platter of ice, basically. So the entropy of that, the number of microstates that would all be seen as this platter of ice, is reduced. Okay, and you also have to take into account that the energy, the heat energy that it released, it's not going to really see that much of that heat energy. Most of the heat energy is going to end up going off into the surroundings, because we're assuming the box is very small compared to the surroundings. So most of the heat energy won't remain in the box. So we can assume, for all intents and purposes, that there is no heat energy that you've released remaining in there, so the temperature remains constant there. Okay, so what we mean when we say the change in entropy of the system is we're assuming temperature, pressure, all of those things remain the same, and all that's happening now is the water molecules are going from the liquid form to the solid form. So we look at what's the entropy of the water in the solid form, what's the entropy of this water in the liquid form, how much does it decrease? Okay, and you find basically that the value is negative 22.0 joules per Kelvin, and it's also per mole. Okay, so per mole of water that freezes, you lose 22 joules per Kelvin of entropy, basically. We're only working with 1 mole of water, so we can ignore that, basically, because basically we just take this times it by 1, and that tells us how much the entropy goes down for 1 mole of water, and that's what we're working with. Okay, now what we need to do is take into account the change in entropy of the surroundings. For this, we need to know how much heat energy is released from 1 mole of water going from being liquid to being solid. And basically, you find that 610 joules of energy are released per mole of water. Okay, so in this case it's 610 joules that are going to be released for a single mole of water. So we can stick this in this term, and then we need to know what the temperature of the surroundings is, and this is how we're going to find out that ice will not freeze unless you're below 0 degrees Celsius, basically. So, if you stick some temperatures in here, so for instance, if we use a positive temperature such as 5 degrees Celsius, and we calculate what the change in the entropy of the universe will be if you undergo this transformation where this water turns to ice in this classroom, and the heat from that reaction goes off into the classroom that's at 5 degrees Celsius, the change in the entropy of the universe will be negative 22.0 plus 610, and now you need to put the temperature in kelvins. Do not put it in degrees Celsius. That's a very strange unit to use for temperature. We just happen to use it all the time. The normal unit for temperature is Kelvin, and to turn degrees Celsius into Kelvin, all you do is you acknowledge that 0 Kelvin is equal to negative 273 degrees Celsius. Okay, so if we want 5 degrees Celsius, then we know that 0 degrees Celsius must be 273 degrees Kelvin, okay? And then if we want 5 degrees Celsius, all we do is add 5 onto 273 to get 278. So I put that under there. Okay, and when I now work this out, what I get is that this number here, 610 over 276, is 21.6. Okay, so when I subtract 22 from that, I get negative 0.4. So the total change in the entropy of the universe will be negative if you went from macrostate 1 to macrostate 2 when the temperature of the classroom was 5 degrees Celsius. Okay, so that's why the ice would not freeze when the temperature of the classroom was 5 degrees Celsius. Whereas, if I now work it out at a negative temperature, and a good number to use is negative 5 degrees Celsius, so let's go for negative 5 degrees Celsius, then again the change in the entropy of the system will still be negative 22.0. Okay, but the change in the entropy of the surroundings will this time be 610 over negative 5 degrees Celsius. That's 10 degrees Celsius lower than 5 degrees Celsius, so that's 268 Kelvin. And if I work out what is 610 over 268, basically I get that it's 22.4. So this time I get that the total change in the entropy of the universe is positive 0.4. Okay, so I get a positive change in the entropy of the universe, and therefore this transformation is allowed by the second law of thermodynamics. Okay, so to summarize, the second law of thermodynamics says that the macro state of the universe will always go from a macro state of low entropy to a macro state of higher entropy. And remember, entropy is a measure. It's not a direct measure, it's this Boltzmann constant times the natural logarithm of the number of microstates. But in principle, it is measuring the number of microstates that the universe can exist in, which would all appear as that macro state. Okay, so basically, it's a very intuitive law. It just says that you will go from a less likely conformation to a slightly more likely conformation over time. So you will just adopt a macrostate which is more likely, basically, has more microstates of the universe which actually would be seen as that macrostate by a macroscopic organism such as a human. Okay, so it's important to understand that the second law of thermodynamics is something that only works because we are dealing with gazillions of molecules. The molecules themselves do not obey the second law of thermodynamics. They do not sit there saying, I can't go over there because entropy will go down. It is a macroscopic law that only works because we are dealing with huge numbers of particles, and then the laws of probability take over.